So, welcome to Bio 1107. In the first part of the course, we're going to look at the building blocks of life, the atoms and the molecules that make up these larger molecules that make up all these cells that make up inherently all of life. So, to start, let's start with some chemistry. For those who've taken chemistry, this might not, you probably know most of this, but just to go over, um, we're talking about atoms in this case. Atoms make up all things, and atoms make up, if you have multiple atoms come together, you have molecules, right? And we're going to talk about both of these, but essentially they can be used interchangeably. Atoms are just pure individual entities, while molecules are atoms put together. And the basic structure of an atom is you have a core called the nucleus, surrounded by electrons, right? Electrons have a negative charge, and in the nucleus we have what are called neutrons and protons. Now, protons are positive, like I said before, electrons are negative, and neutrons, as the name suggests, are neutral, right? So overall, because you have neutral and positive, your nucleus is positive. You have a positive charge. Let me use a different color. So your nucleus has a positive charge, and your outside electrons have a negative charge. And that's basically how we look at atoms. And we can arrange all the atoms found in life in a way that looks somewhat like this. So if I kind of scroll down, this is what we call a periodic table. This is an incredibly simplified version of the periodic table. But a full periodic table would also have numbers on the side like this. So for hydrogen, you would see 1, 1, and let's say for carbon, you would see 12, 6. All these numbers mean are that the bottom number, or typically the smaller number, is the atomic number. The atomic number is basically what defines this atom here. And it's also the number of protons it has. So carbon has 6 protons, and nitrogen here has 7, oxygen has 8. And we defined atoms based on the number of protons they have, these guys. And this 12 up here, this is the mass number. That's how much it weighs. And we define the mass of atoms based on their neutrons and their protons. And they're both worth essentially 1 mass unit. So essentially you can deduce that if carbon has 6 protons and a total of 12 mass units, and protons and neutrons both weigh the same essentially, then you can assume that it must have 6 protons plus blank neutrons equals 12 mass. And we, in this case, can deduce that there must be 6 neutrons in carbon. And another thing we want to talk about here is this factor called valence. You'll learn this much more in chemistry, but when we talk about atoms, there are different layers to these electrons. And valence deals with the electrons on the outmost layer, this layer right here. And we talk about how many electrons it has, because the valence has a lot to do with the atom's ability to react with other atoms. So for example, sodium, if you look how there's different layers, on the most outside layer, there's only 1 electron. So we give it a valence of 1. Magnesium, as you can see here, has 2, all the way up to argon, which has a full 8. 2, 4, 6, 8 round. So valence is the number of bonds it can make. So it's the number of lone pair electrons. So as you can see, there's 1 lone pair by itself. It can have a friend basically. Here we have 2 lone pairs, 3 lone pairs, up to 4 lone pairs, which is maxed out silicon and carbon. And then once you go to nitrogen, you have, you can't really see, but these 2 are paired up. So now we can only count 1, 2, 3. 3 lone pairs. Oxygen, these 2 are now paired up, so we have 1, 2, 2 lone pairs. And that's basically the pattern. So that's your valence. So valence electrons is the amount of electrons on an outermost shell. Your valence is the number of lone pair valence electrons. Another property we want to talk about is this property of electronegativity. Once again, if you took chemistry, you should know all this. But all electronegativity means is how badly something wants electrons. All right, and the general thing we talk about is if you exclude this group right here, don't worry about these guys, right? Let me switch colors. From fluorine, fluorine is the absolute most electronegative thing on the periodic table. And as you move this way to the right and this way up, you get more electronegative, right? So fluorine is more electronegative than oxygen, which is more electronegative than nitrogen, which is more electronegative than carbon. And for all intents and purposes, because you won't go into that many atoms in this course, the thing to know that I would take careful remark with electronegativity is that oxygen and nitrogen are much more electronegative than carbon and hydrogen. So basically, carbon and hydrogen, although they look very far apart, have around the same amount of electronegativity. So when we talk about bonds later, we'll understand that carbon and hydrogen make things that are really nonpolar, whereas these guys, oxygen and nitrogen, make things that are much, much more polar. So next part of the chemistry we'll go over is bonding. How we turn these atoms into molecules. And that's when atoms have to bond to become molecules. So the first type of bonding I want to talk about is ionic. The base word of this is ions. Ions, if you're chemistry, you know that are molecules or atoms, or atoms or molecules with a charge, so either plus or negative. All right. So the classical ionic bond is that with salt, sodium chloride, all right, NaCl. And what we talk about is Na has a valence. If we go back up here, oh, sorry about that. If we go back up here, has a valence of 1. Chloride also has a valence of 1. So they match up very nicely. So what happens is, let me switch back here. Sodium has 1 valence electron here, 1 unpaired. Chloride has 1, this has 2 paired, 3 paired, and then 1 lone one. So and chloride, as you saw, is all the way in this corner of the, in the top right corner of the periodic table. So chloride is much more electronegative. It wants electrons much more than this sodium. So what it will do is it will take this sodium and just rip it and give it to itself. All right. So what happens when that happens? Now we have sodium, but this electron was negative. Now it lost this electron. So if you take away something that's negative, if you minus a negative, what happens? You essentially add, right? So this sodium now has a plus charge. It is positive. It is a positive ion. This chloride now gained something that was negative. If you get more negative, you become negative. So this chloride is now negative. And to simplify things, you know that opposites attract. So what happens is this sodium now wants to be with that nitrogen. So if I switch to a new color, now we have this NaCl, this being the negative portion, this being the positive portion. And they will stick together like salt crystals. The next type of bond we'll talk about is, let me go back to black, covalent bonds. Covalent bonds. And the thing about covalent, well, okay, so backtrack. The thing about ionic you want to think about is this give and take, right? This chloride took an electron and this sodium gave an electron. That's how things, that's the defining feature of these ionic bonds. Now when we talk about covalent, now we're talking about sharing, right? Sharing of these electrons. And the common covalent bond we want to talk about is hydrogen. Hydrogen normally has one electron, and this hydrogen has one electron, right? Instead of giving electrons, electrons want to be paired, right? So if I gave this guy here, he would now be paired. This guy would have nothing at all. That's unhappy. That's not covalent bonding. Covalent bonding is when this hydrogen says, hey, I have this electron in the ring. Why don't we come together and put our rings together? So essentially it forms one really, really big cycle. So to better illustrate it, from the perspective, so one of these belong to this one belongs to that one, right? But from each perspective, they're sharing them. So from his perspective, he sees 2 electrons. And from this hydrogen's perspective, it sees 2 electrons, right? So it's sharing. These electrons are distributed evenly amongst both nuclei. So it's very happy. Does that make sense? It's shared. And we typically draw one of these. This line symbolizes 2 electrons. Now, there are 2 types of covalent bonding. There is polar and there's nonpolar. So given an example of nonpolar is this hydrogen, where in this bond, both of these nuclei are the same electronegativity. So they want the electron just as much as each other. So the electron is going to spend as much time with each because they're very equal. It's very nonpolar. There's no pole. Another example would be methane, which is carbon surrounded by 4 hydrogens. Like I said earlier, carbon and hydrogen have around the same electronegativity. So if I look at any one of these bonds, it's going to be very even because it says, hey, do I want to be, so there's 2 electrons in both these bonds. Now it looks like the division sign. Okay, so each of these electrons say, hey, I could either be with carbon or I could be with hydrogen. They both want me as badly, so I'll spend about the same amount of time with each. So they're very non-polar. There's no pole. If I look in this bond, all these bonds, they're very even, right? And you'll understand what a pole is when I talk about a polar bond. So your classical polar bond is going to be water, H2O. So you have the oxygen in the middle connected by 2 hydrogens. And if we remember the periodic table, you know that oxygen is much more right of the periodic table than hydrogen, which means it's much more electronegative. So before, where we had these 2 bonds, say here, right, this hydrogen says no, 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 no. Don't share like here. I want these electrons much worse, much more badly than these hydrogens. Give me more electrons, right? So what it more looks like is, in green, like this, right? Because the oxygen wants the electrons more. And as we know, electrons are negative. They have a negative charge. So what happens is this oxygen has a partial negative charge, and the hydrogen has a partial positive charge. And there's a really weird Greek letter that we describe when doing this. Don't worry about that too much. But just understand this means partial charges. And so this is different from the NaCl, where this completely took all the electrons. This had completely positive charge, completely negative charge, and that's why they're stuck together like magnets. Here, there's an actual bond. There's an actual sharing of these electrons. This hydrogen will still see 2 electrons. This hydrogen will still see 2 electrons. It just so happens that the electrons are typically much more closer to this oxygen. So if I look at this overall molecule, if I look at it from far away like this, I'll find that there is a negative side and a positive side. And these are what we call their poles, right? These are poles, which means this molecule is polar, right? If I look at this guy from far away, I see this, but there's nothing particular about any region. All these regions have the same charge, basically. So this is what we call a non-polar molecule. And this polarity of water, understand, if you can take one thing from this lecture, understand that water is polar. That is the most important thing. And in my next lesson, I'll talk about why it's so important that water is polar, because that does give water all its important properties. So to backtrack, nonpolar, polar bonds defined by the atoms they have. Ionic bond is a give and take. Understand the level of polarity. Carbon and hydrogen aren't that polar, but oxygen, nitrogen, fluorine are more polar. If I keep going up, delete itself. But yeah, understand what valence is. Valence is the amount of lone pair electrons. Things with the same valence tend to interact with each other. Understand what valence electron means. It's the electrons on the outside. And understand that the smaller number, the atomic number, defines a atom's amount of protons. The larger number, or the number on top, is the number that defines its mass, which is the number of neutrons and protons added together. Understand that things going up and to the right are more electronegative. And that's about it. So I'll catch you for my next lesson about water. All right, thanks guys.